Hi, I'm Postcard Professor Primary 6 from Yumin Primary School. For this time, still at ordinary differential equations. But in ordinary differential equations, we have already many lessons about it. You have learned some of these methods that we could use, but we're going to learn much more. But when we learn all these extras, that means we still need to revise and summarize what we have learned from the past methods. In fact, we still have to make comparisons to show us in each different method what's so special about them. Okay, so first for this part, when I was using Chinese to explain about this, let me explain how we arrive at this ordinary differential equations. So right now here, I'm going to use English to explain that again. Okay, first for this part here, let's just say we start from a thing that every single child would know about it. Every single one. It can be from the four operations: plus, minus, times, divided. In equality. For this equality, we can just be simple statements. But what's so special about this? How can we arrive at something different? For example, we can change the sign, not the plus or minus or some others. Or it can be the equal sign. If we change the equal sign, so then we'll get something called we change this equal sign, we get something called inequalities. Okay, we get this thing called inequality. And what if we change it a little bit more? Like from these equalities, we change it into like just with maybe two variables. For example, x minus y, then the whole thing squared. So what do you get? You get x squared minus 2xy plus y squared. But what are all those? Those are called permanent identities. But permanent identities, they're actually this type of equality. Okay, so for this part, you get your permanent identity. So what next from this equality? From this equality, how about we change it a little bit? Here is we change the equal sign. Here is we change it into two variables. Like you make an operation of these two variables, they'll get something. How about we change it a little bit? So we change it, for example, in one variable. One variable plus something is equal to something. And that means it will be an equation. So from this part, you can arrive at equations. when you arrive at these equations, the next thing you can have, well, like from these equations, it's just like, for example, x plus 3 is equal to 5. So then you can just find x equals to 2. From equations, what if you like just change it a little bit? You add another variable itself. For example, x plus y is 5. But then x and y, of course, still have infinite solutions. So those, we change the form, x plus y equals 5 into y is equal to negative x plus 5. Okay, that's just one of these examples. So then you get functions. These are functions. Then from these equations and functions, you can actually get the locus equation. Well, these parts you get locus equation. Now from these locus equations, but when you get from equations and functions, they're actually not much of a difference. There are no significant differences, but there is still a little bit of a difference. Like when you get from equation, you'll most likely get an implicit form of this locus equation. But if you get it from these functions, you get an explicit, just like most likely get an explicit form of this locus equation. But then, equations, functions, and locus equations, we can make an operation to change them all into something. This is ordinary differential equations. These differential equations, they still have to be differentiation. So there must be this differentiation. Okay, here from all of these three, you can make a differentiation and get like a derivative. But then next part, differential equations. Let me say this, a combination of this differentiation and this equation. And this is your differential equations. Okay, but did you realize one of these differences here? From this part, equality, from the main thing that we started from. But did you realize this blue path over here? Well, it's actually, like you can call it the main course. It's like what it mainly comes from. From equality to equation to this differential equation. Okay, so this is about what? Where is it from? Okay, so this is what we have done for the lesson when I was explaining in Chinese. But in this differential equations, how about those methods that we have learned before? Where did they all started from? Okay, so from this part, okay, just take another quick look at this as I'm going to use this space. Okay. So for all these ordinary differential equations, we can write it as f includes this x, includes y first derivative, y second derivative, and so on. And this is c. So for this whole of this ordinary differential equation, it might be linear. It might be possible. How about homogeneous? Okay, these two might not be, but if this is homogeneous, I can give examples, like one of these examples of it. But except that it's using f. So this function of x, f and x, what if it times this y nth derivative, then add f, then n minus 1 x, then y n minus 1 derivative, times it plus until f 1x. Well, here is still y first derivative, so then we still need to go on to f0x, but it is still another function of x, and this to be homogeneous is 0. But in this form, rather than as n and n, these two are corresponding, as we can write it into this sigma notation. So this m from here, 0, starts from 0, all the way until here, n. So it's from 0 until n. So that means at this part, you just put f m x, then it's y m derivative. Okay, if you want to write it in sigma notation, it will become this form. Okay, so this is one example of this homogeneous ordinary differential equation. Next part. How about its coefficients? What if it is a constant coefficient? It might be constant coefficients. Then, but must this be an ordinary differential equation? Must it be an ordinary differential equation? It might not be. This is just a differential equation. So what if it is ordinary differential equation? What if it is partial differential equation? Then next, how about its order? Because this order can be first derivative, second derivative, third derivative, and it goes on. It can be whatever's derivative. So these are different forms of it. So firstly over here, let's start from the most basic form that we did at first. Okay, so this part I'm going to erase it. So from these, we'll start from the simplest types of ordinary differential equations. For example, px dx, and this is equal to qy dy. Okay, so that means all these x are on one side and all these y on the other side. So that means they're all separate. So for this type of ordinary differential equations, we call it the separable differential equations. So for all these different separable differential equations, we can also give some examples, like dy dx, then you plus gx, then y, and this is equal to 0. Then at this part, with these, you move this to the other side, then some parts you divide back. Then after that, we'll integrate on both sides, same as for these two cases. We'll integrate on both sides. But this integration that we normally use is actually indefinite integration. In indefinite integration, some of these we might not be able to solve. But even in definite integration, we also might not be able to solve. But in definite integration, it has to be under some special range. And only under this special range, we can use some of these special methods. For example, the beta function, the gamma function, all these special functions, double integration, and the theory of complex variables, all these, and so on. Then that means after these, but even if we can just integrate with these inside, we can use the basic integration formulae. We can use the 3 basic methods, and those are partial fractions, substitution, and integral by parts. These different types of methods we can use on this integration. But let's think about this. Here is only all x on one side, all y on one side. We can separate this x and y. We can separate it. But what if we cannot separate it? If we cannot separate it, then what we'll think of next will actually be p xy. Okay, p xy. Then after that, dx. And then this is equal to, the other one will be q xy. Then dy. But this form is when we cannot separate it. X and y cannot be separated apart. So what will come to our mind next will actually be that this is the total differentiation. We have to use this total differentiation as they cannot be separated. And under this total differentiation, the form of this total differentiation, the form of this total differentiation, you actually write it just like the df. So this is the form of the total differentiation. So that means for all these different parts, we can try to change it into some form like this with this f. But there must be another condition that we must satisfy. Okay, let me just write it out. And this parts that it must satisfy is the mixed partial differentiation. So whether with respect to x first or y first, they're all the same. Okay, so that condition must apply to this part. Then next, we have this part. And we actually want to have this part. But all of those other remaining parts, you might have some other random parts. So then from this, you still have to integrate all the others. So these forms might be like this, just a function of x or just a function of y. Therefore, it's just these kinds of simple integration. So far from here, these two differences are actually just total differentiation. You cannot separate the x and y apart. But for separable differential equation, you can separate the x and y. But from this total differentiation, you still must get this part.